In this presentation, we're going to continue on with non-parametric statistics. Now, this is part B of a presentation where a psychologist is investigating aural and visual memory. Okay, so this is the second part. In the first part, we essentially had a look at the sign test. So we're going to go on and have a look at another procedure here shortly. So let's read the question. After completing this experiment, the psychologist decides to investigate whether the aural memory scores can be improved by coaching. A second experiment is conducted, the first one being in part A of the question, in which a random sample of 12 students performs an aural memory test before and after several sessions of coaching in skills believed to aid aural memory. And here are the two tests. So this is the before and after, so it's paired data here. So an improvement here and an improvement here goes down here, that's a negative, okay, and so on. Now, what you'll notice is that for most of the students here, that they do have small increases or small decreases, but there are some very big jumps here. This is plus 24 and plus 15, whereas we're going very small jumps elsewhere, okay? So essentially what we're thinking here is the data is going to be very skewed. Okay. So anyway, let's read the question. It is required to test whether aural memory is improved using a non-parametric test. Explain why it's not satisfactory to use a test similar to the one in part A, which is the sign test. Carry out an appropriate non-parametric test. Okay. And it is suggested that non-parametric test would be more appropriate to analyze the data without performing the analysis. State which test you would assume and any assumptions necessary for this analysis to be valid, and will these assumptions be reasonable in this case. Okay, whoops, I'm going a bit crazy there with that thing. So let's go down. So I just paused it and unpaused it, so I'm just back now. So essentially what we did in part A was the sign test, and essentially the sign test actually was sort of based on categories, A or B, plus or minus, binomial categories. It is not very powerful, and particularly the sample size here, now the sample size being referring to part A, which is 10, not 12 here in part B, is not large enough to make for effective use. It's not large enough to make inferences around the population, general population, okay? So the data provides information, and this is part B now, and this should we say provides, I apologize, information which the sign test would not use, namely measuring the change on a numeric scale, okay? This is now talking about part B here, okay? And essentially what we are discussing here is these differences here. So 39 to 63, that's a difference of 24, okay? This is a difference of plus 5, minus 1. These are important pieces of information, okay, that the sign test doesn't use, but we try and use a test that is as powerful and uses as much of the information as possible, okay? So in this case, what we're going to use here is, as well as the sign of the change, we're going to use the magnitude. And so this is what we're going to use. This is the basis of this presentation, really. A Wilcoxon signed rank test is suitable here, okay? So just based on the data before, I actually should have included the raw data, but it's up there. So this is 5 and 6. This is like 39 to 63, and that's a difference of plus 24. So essentially what I've done here is I'll just do one or two here. 7, that's plus 7, minus 2, plus 6, plus 4, plus 24, and so on, right down to the end, okay? So here I am again, and that's just picking up where I left off the last one, okay? Now, what I'm going to do here is I'm just going to sort of highlight where we have negative signs, negative differences here. Okay, so here we have 3 negative differences. Okay, and the rest are all positive differences from after. Okay, so now what I'm going to do here also is I'm going to get the absolute value of these differences. Okay, so just disregard the sign. That's the absolute value sign of the difference there. Okay, so they're, yeah. Now what I will also do here is I will rank them. Okay, now this actually requires a little bit of number crunching. For example, we got two differences of 1 and 1. Okay, absolute differences actually, I should say, here and here. And we got a couple of, we've only got one situation where it's a difference of 2, an absolute difference of 2, which is here. And work through it the whole way through. Okay, so what I'm going to do now is I'm going to rank these differences. And in the case of draws or ties, I will just give them the average of the two rankings. So let's just say I have a rank, these are my first and second jointly. So what I'm going to do there is both give them a rank of 1.5. Okay, 1.5 being the average of 1 and 2, seeing as these are the top two. Okay, then I'm going to go to the third ranking value here, which is 3, and so on, and work the whole way through. 4, this is the 4th highest rank, 5th highest rank, 6th and 7th, 8th, we have a 9th and a 10th there, or sorry, a 9 and 10. We have a tie there for positions 9 and 10, so we give them both 9.5, and then 11 and 12. Okay, so we rank them up like that, and you notice actually we start from the lowest difference upwards. Okay, that's an important little remark there. We start from the lowest difference upwards and work up. So the lowest difference there in terms of absolute difference is 1 and 1. Okay, now, so what we're going to do here now is we're going to remember which of our differences were negative. These ones here. Okay, so let's check out the corresponding ranks. 6.5, 9.5, and 1.5. Okay, 3 plus 6.5 plus 9.5 plus 1.5. Those are the sums of the ranks for the negative differences. Okay, when we look at the absolute differences there. Okay, so that's important. What does that work out to be? 20.5. Okay, now if you do it for the positive ranks as well, it should work out to be 57.5 or 57.5. Okay, so sorry, the null hypothesis is that the Aural memory scores are not altered by coaching. The alternative hypothesis is they are improved by coaching, and a one-sided test is required. Now, I actually made mention of this previously, and it's really in part A, but it was part B. It was where I really wanted to talk about it, because this is relevant for when we use the tables. Okay. Now, what we're going to do here is we would work out both of these values here, and essentially what I do there is go through the whole thing again, just to be doubly sure. We would work out 9.5. We'd work out these ones here. Okay, 9.5 plus 8 plus 5 plus 12, and so on, and that would give us 57.5. Okay, so you just pick out which of those two values is the lower of the two, the minimum of the two, and in that case it is 20.5. Okay, now we're going to the tables here. So n equal to 12 gives 17 as the critical value for a one-sided 5% significance test. Now this is important here. So the tables should look like this. Now, these are two-sided tables, okay? And we're doing a one-sided test for 5% significance level, okay? But these tables here are two-sided tables. So what we do here is we actually would go to this column here, okay, the 10% column, okay, and here it is. So our critical value there is 17, okay. So essentially, why do we go to the 10% one? It's 5% for each tail. So it's 10% over two tails, 5% for each tail. And we're dealing with a one-sided test, so this gives us the value that we are looking for the critical value that we're looking for, which is 17. Okay. So tables for n equals 12 gives 17 as critical value for a one-sided 5% test. So in this case, the test statistic has to be less than 17. So in this case, there is not enough evidence to reject the null hypothesis. Okay. Now, so the other question was actually related to pair sample t-test. Using the differences would be appropriate if the distribution appeared to be approximately normally distributed, but that actually was unlikely. We looked like we have two very high values on the same side, and it essentially looked a bit skewed, so it didn't look like a good choice to use so we had two values that really skewed it, skewed the distribution. Okay, so that would really undermine the assumption of normality. Although the fact is the t-test is actually quite robust to this, but essentially what we're here to do is learn about non-parametric tests. So anyway, we'll leave it there.